We want to find reactions at A and at C for this one. We're given the diagram, and that B is smooth. Okay, so we can jump right to these individual members' free body diagrams. So I'm going to start with member AB. It just looks simpler, so I'll start with that. So on member AB, first of all, this distance is 0.8 meters. I have one external load acting on A. I have this 900 Newton meter moment acting at A. Right, so that's the only external load acting on it, or applied load acting on it. At point A, I have a pin, like we've seen before, so I can model that as an AX to the right, and I can model it as an AY up. Just looking at member AB, when it's connected at B, it can move along the length of the slot, which is also the length of AB, but it can't move perpendicular. So it's prevented from moving perpendicular, so there's going to be a force perpendicular to the slot, which is also perpendicular to AB. All right, so we know its direction. It's a single force. I'm going to call it B. I'm making an assumption that it's up and to the left. It could very well be down and to the right. All I know is it has to be along this axis. And I also know that this axis is going to be 45 degrees from the vertical. All right, so one force with a known direction. So we know more information than if it were a pin, where it would just be a Bx and a By, which would introduce two unknowns. All right, questions about the first free body diagram? So from picture number 1, we have 3 unknowns in this picture, so it's potentially solvable. So I'm going to go to the equation step and then come back to draw another picture. C doesn't even appear in the picture, so we won't be able to solve for C. So we'll get that in another picture. So based on how the picture is set up, I'm actually going to start with the moment about a point, just so I can start to get numbers right away. So since this is already here, I'll just kind of reuse this. So I'll start with the moment about a point. What point should I take the moment about, or is best for me to take the moment about? A. Right, A, it's only going to be in one picture, and it's a pin. So what's my right-hand side for what will be equation number 3? Right, so both of them simultaneously. The first one I heard was negative 900. So from that applied load that is going to be clockwise, we make again the assumption of positive being counterclockwise. So negative 900 Newton meters. And then, right, what you said, the positive 0.8 times B. This is a somewhat rarer occurrence when we take a moment. We actually do know the perpendicular distance between the force B and the point A, because B is perpendicular to this distance. If B were not perpendicular, then we would have to do what we normally do and split it into a positive and a vertical component, and then we need this vertical component and this horizontal component and do it that way. Here we can go right away. We know the perpendicular distance is 0.8 and save ourselves a lot of trouble by doing it that way. So very simply, it'll be 0.8 times B. If you want to go through the steps and split into horizontal, vertical components, it'll end up still giving you 0.8 times B. So from equation 3, because of where we took the moment, we can find the value of B. To 3 digits is 1,130 newtons. I'll reiterate, I made the assumption B was up and to the left. It turned out that it was, that was the correct direction. I could have also assumed down and to the right, and we'll see what the implication of that would be in the second picture. Neither one would be wrong. We just have to pay attention to the sign we got out of the equation we wrote. So I'm going to go to picture number 2. So we have one applied load of 500 newtons. Right, so it's a built-in connection. We can model that as a Cx, Cy, and a moment, which I will call M sub C, and assume it's positive. I'm assuming all positive at C. And then what else do we need on the picture? Right, we need B. So this was modeling what BC was doing to A. So this is going to model what AB does to BC. I assumed up and to the left here, so I must draw this as down and to the right. Same value, opposite direction. Since I am looking for the reactions at A, I'll solve this before I get to the next step. So the only forces acting on picture 1 are AX and B, or in the X direction, and AY and B in the Y direction. So since I now know the value of B, I can put that into equation 1 and get AX. So I should get 795 newtons up. And AY, I should get a negative 795 newtons, which means my assumption was wrong. To the right. Negative 795 newtons, my assumption was wrong, so it's actually down. All right, so we have our AX, we have our AY. Now we can move on to the rest of our equations here. So in the X direction now in picture 2, I'm going to have positive B sine 45 plus Cx. I know B from equation 3. So Cx is going to be a negative 795 newtons. I assumed it was to the right. It's therefore actually to the left. In the y direction, I'm going to have my Cy minus 500 minus B cosine 45. So again, I can use this value of B. Cy is 1,300 newtons up. So in my sixth equation, what point should I take the moment about? C, it's a built-in connection, so it gets rid of Cx, Cy, and it only appears in picture number 2. So if I take the moment about C, I'm going to have, this is going to be equal to this reaction couple MC. Do not confuse. This just means it's a couple. Sum of moments about C is what this means. These are not the same thing. So unfortunately, the notation is a little bit redundant looking. This is a couple. This is saying I'm taking the sum of all the things that contribute to the moment about C. One of those things is what I'm calling M sub C. I assumed it was positive, so it's going to be a positive MC plus 0.6 times the 500 plus the vertical component of B. So that's going to be B cosine 45 times 1.2. And the horizontal component of B has its line of action pass through C, so it will not be counted in equation number 6. So in equation number 6, again, I know B from equation number 3. So we use it once again in equation number 6. So that leaves the only unknown, that couple from the wall onto member BC, what I called M sub C, is going to be negative 1250 Newton meters. My assumption was that the wall was applying a counterclockwise moment on BC. It's actually I assumed counterclockwise. It's actually clockwise. So these are the 3 reactions I have at C and the 2 reactions I have at A.